What's up, calculus students? You can see me. Yeah, this is a homework video I'm recording this year. Uh, New technology. So we are going to do what is created as a new lesson 2 homework, this accumulation function homework, second fundamental theorem of calculus homework. I'm hoping my cursor comes back on, and then we'll get started. So we have this accumulation function g of x, which is the area under f from -3 to x. This is like questions that we've seen before where this is f prime and they said like, hey, what's going on with f? But what we now know is that the area under a derivative equals the amount of change of f. So it's like if we are given an initial condition like f of -3 is 0, we would be able to calculate some areas to figure out other function values. Now, it doesn't look like f prime, and here's f, and here's an initial condition. Instead, they kind of throw that all together by saying, hey, this is f, g, which ends up being the antiderivative of f, is equal to the accumulated area from -3 to x under f. It's the same thing. Only instead of like giving you the initial condition, it says like, well, if you start at -3, you know g of -3, which is the integral from -3 to 3 of f, that's going to be 0. Like an area from a point to the same point is 0. So that's like my initial condition. And then we can like add my areas to figure out these values of g, which you can consider f if this is f prime. It's the same stuff that we've been doing. It's just almost like a level up. G is actually the antiderivative of f. We can say little g is actually big F. But whatever, if like that's confusing to you, it's okay. You'll be fine as long as we understand how to find areas, like g of -5. If we understand that going right to left is like going backwards in time, it's going to be the opposite displacement as if we go left to right. If I go from -3 to -5, this area here, which is a triangle, base 2, height 2, so this is going to be +2. But since I'm going from right to left, I need to go backwards in time. That's like, okay, well, I've gone to the right 2. Well, now, like going backwards, it's like I've gone left 2 from -3 to -5. Let's do some others. G of 2, area from -3 to 2. And unlike in the past, like we use our calculator to find these, here I'm going to ask you to find the areas by hand because they're all like line segments. So I got 1, 2, 3, 1, 2, 3, 4. So 1/2 base of 3, height of 4 is going to be 6. 2 times 3. Here, base of 2, height of 4, this is going to be an area of 4. And this is a base of 2, height of -4. That's an area of -4. So from -3 to 2, it's going to be 10. Hopefully my thing froze again. It'll come back. And we're going from left to right, so that's why it's +10. G of 4, so that's going to be the area under f from -3 to 4. And that is 6 plus 4 minus 4, which is 6. Now, the next questions come from the derivatives. Well, again, it's like if this was f, and it's like, hey, what's f prime of -3? Well, this would be like the graph of f prime. This is like you're given the graph of the derivative. But like this is g. They're asking you, what is the derivative of g? Well, the derivative of g is just f. We talked about in class how this accumulation function, the derivative of the area, the derivative of the antiderivative is just f. G prime is just f. That means g double prime is just going to be f prime. So if you're asked for g prime of -3, it's simple. It's the same as f of -3, right? No big deal. This is f. F of -3 is 0. That y coordinate of f at -3 is 0. G prime of -1 will be the same as f of -1. Now I have to do a little bit of work of finding this value. You got to use the slope. Well, I go up 1, 2, 3, 4. The slope of this line segment is up 4 over 3. That's the same as going up 1 over 4/3, or going up up 1 over 3/4, or going up 4/3 over 1. So it's either up 4 over 3, or you could say, okay, I'm going up 4/3 when I get to 1 over. So this point right here is not at 1. This point is actually at 4/3, which means if I go over another 1, I'm going to be going up another 4/3, gets me to 8/3. It's not a specific value, and we need to be comfortable with this, like applying a slope to finding a value. So up 4/3, I get to 4/3. Up another 4/3, I get to 8/3. Up another 4/3, I get to 12/3. Well, that's 4. That works out. So f of 1 is 8/3, and you need to be like cool with getting that value 8/3. G prime of 1 is just equal to f of 1. Same deal, I need to find this point at 1. Well, this slope is down 4 over 2, so the slope is down 2 over 1. So I go down 2 over 1. I go 4 down to 2. This is easier to calculate than this. But again, it's just applying a slope, not assuming that the values end up at whole numbers. Important. G prime of -5 is the same as f of -5. F of -5, 1, 2, 3, 4, 5 is 2. Okay, next question. G double prime. Okay, well, again, understanding that this is like f primes to this f, understanding that G is the antiderivative of f, G double prime would be like big F double prime. Well, it's just like regular f prime. If you don't get that, that's fine, as long as you kind of stick with this, like the derivative of an integral is just what's inside. The derivative of that is f prime. G double prime equals f prime. So G double prime of -3 is f prime of -3. Now, f prime, you're given f. F prime is a derivative. It's a slope of a tangent. It's a rate of change. You need to find the slope of the tangent at -3. Well, look, it's a sharp point. This is the only time I hope that I say this. This sharp point, you don't have a tangent slope. This value is undefined. Why? Because it's a sharp point. We're not going to eliminate it from like a possible contender for like a point of inflection or something like that for G, but we'll say that the value is undefined. G double prime of -1 is the same as f prime of -1. At -1, what is the slope of f? Well, we talked about earlier, it's 4/3. G double prime of 2 is f prime of 2. F prime of 2, 1, 2. So the slope, not the value, the slope of this line segment is -2. Okay, so that's what you have to do. Find the locations of the relative max min of G. So again, this is again just like what we've done back in the day, back in Unit 4, when it's like, hey, this is f prime. What are the max and mins of f? And you do a sign analysis of f prime. You look at when things are positive or negative. This is like a velocity. Okay, you look at when velocity changes sign to figure out when you're moving to the right or left, or we're looking at when f prime changes sign to figure out when f is increasing or decreasing. You're not looking at slopes for this. You're looking at values. So relative maximum min, or G, I'm going to analyze G prime. Well, G prime is the same as f. So I'm going to, on a number line, look at the signs of f. Okay, f is positive. It's got a 0 at -3, but it doesn't change signs. It's an interesting point. So positive, it's got a 0 at -3, but then it goes back to positive. And then here, f is 0. So that means G prime is 0 at 2. So at 2, G prime is 0, and then it's negative. That is telling me that x equals 2 is a relative max of G. I also know it's going to be the absolute max location because I'm just like, G is going to be increasing, flattening out, increasing, then decreasing. So I know for a fact that at 2, we're going to reach our highest value for G. And we're going to be able to find that value. That's the next question. What is the absolute max value and the absolute min value? I don't have any relative mins here. So the min, the actual like absolute min is going to have to come at an endpoint. I'm going to have to check, but I'm pretty sure I know what the answer is going to be. So I know the max because G prime, which equals F, is positive until 2, and then it's negative from 2 to 4. Is it 2 to 4? Yeah, from 2 to 4. Since that occurs, I know x equals 2 is the max, the absolute max. I need to find G of 2. I found G of 2 earlier. G of 2 is 10. So that will be the absolute maximum value. It's the integral from negative 3 to 2. 6 plus 4, 10. The area under this derivative gives me my change in my total. I started, my initial condition that is given to me is that negative 3 is our 0. So that's like our initial value. Adding 10 to 0, 10. Now the min is going to be either at the endpoint x equals negative 5 or x equals 4. Now I know for a fact it's got to be at this negative 5. Why? If this is a 0 and f is positive or G prime is positive from negative 2 to 0, that means I start 2 below 0. I start at negative 2, which I already found, and I will increase 2 to get to 0. I will then increase 10 more to get to 10, and then I will decrease 4. The area under this derivative gives me my change in my total. So it's got to be here at negative 2 is my minimum value because I'm only increasing 2. I start at negative 2. I get to 0. I get to 10 by x equals 2. And then I drop down to 6 by x equals 4. I've already found these values. G of negative 5 is negative 2. Again, you're going opposite because we know like G of negative 3 is 0. This area 2 means I've gone up 2 or I've gone right 2 to get to 0, which means I started at negative 2. It's the opposite if you're going from negative 3 to negative 5 as is if you're going from negative 5 to negative 3. And then my other endpoint, just to make sure I know, 4, which I found was 6. That's out. This wins. You can either just check the endpoints and compare the values as a justification, or, and this is because since there's no relative mins, or you can reference the areas. You can reference the displacement. The displacement from negative 3 to 4 is 6, which is bigger than the displacement from negative 5 to negative 3, which is only 2. So like I go up 2, and then I go end up 6 over the course of from negative 3 to 4, up 10, down 4. That's up 6. Points of inflection for G. And after we do this, we can do a very, very good job of graphing what G looks like. So points of inflection, remember we look at a second derivative, G double prime. It's the same as F prime in this case. So it's like the slopes of the tangents. Again, if you thought about this as like this is the graph of F prime, looking at points of inflection looks at when things change directions. Well, let's look at our graph. The slopes of F, which are F prime values, are negative. This slope is negative until negative 3. Now at negative 3, it's not 0. It's undefined. I don't know what the value is because it's a sharp point. That's okay because the slopes are negative and then the slopes change to positive. They are positive until we get to 0. The slope of this line segment is positive. So f prime is positive until 0, and then f prime is negative after that. At 0, again, we don't have like a flattening out. It's a sharp point, which means it's an undefined value, but that's okay. X equals -3 and 0 are our points of inflection on G. Okay? Why? Because G double prime, which equals f prime, changes sign. And just for fun, let's throw this and this together to graph. I already have a bunch of points. At -5, I'm at a y coordinate of -2. So now I'm graphing G. At -5, this is, I'm actually more, I go from -5 to 4, so it should be like this. So at -5, I'm at the y coordinate of -2. At -3, I'm at a y coordinate of 0. At 0, I know I'm going to be at a y coordinate of 6. At 2, I'm at a y coordinate of 10. And then at 4, I'm at a y coordinate of 6. 10 minus 4. That area tells me my displacement. So I'm back down to 6. It makes sense. I'm going up, I'm going up, I'm going down. So going up, go up, go up, go down. But this tells me my concavity. This is telling me from -5 to -3, G is concave down. So I'm actually going to be going up, but concave down. Okay, then I'm going up, concave up until 0. Then from 6 to 10, from 0 to 2, I'm going to up, concave down. And then I will start going down, concave down. In the past, we were unable to do such an accurate job of sketching what F looked like given F prime, because we didn't know the fact that areas under F prime told us changes in F. So in the past, what we did was kind of just like threw this down, and we were like, okay, this is F prime. We threw this down. This is F double prime. This is negative until -3, which is positive, until 0, which is negative. And then we just kind of said, here's what the shape looks like. Increasing concave down, increasing concave up, increasing concave down, decreasing concave up. And we like threw those pieces together willy-nilly. We did not know how much to go up. We didn't know how much to go up from here to here, how much to go up from here to here, from here to here, how much to go down. Because we didn't know, and we know now, that areas under a derivative gives me total changes in like the antiderivative in the original. Okay, so this is important stuff to know. Like areas under derivatives, changes in totals. That's the fundamental theorem of calculus. All right, changing things up, it's going to be a little bit more complicated because now I have something other than just an integral. I have 2x plus this integral. And it makes the calculations more complicated. It makes understanding what's going on more complicated than just like, where do I start? Because the initial condition is not just like, oh, if I plugged in -3, I get 0. Because if I plugged in -3, this gets plugged in a -3, it gets -6, and this is 0. So we have to do a little bit more work, a little bit more analysis because of the fact that we have this 2x. So this is like, hey, be careful. Ready? H of -5. 2 times -5 plus area from -3 to -5. This is the same graph, so let's just throw this down. This is 2, 6, 4, -4. So this is -10 plus -3 to -5 is the opposite, Going backwards, it's not positive 2, it's negative 2. So h of negative 5 is negative 12. We're going to use that value in the future. H of negative 3, 2 times negative 3 plus the integral from negative 3 to negative 3. That's a 0 area starting at some place, staying at that place. H of negative 3 is just going to be negative 6, or negative 6 plus 0. H of 0, 2 times 0 plus negative 3 to 0, f. 0 plus negative 3 to 0, area under the derivative, change in our total, 6. H of 4, 2 times 4 plus integral from negative 3 to 4. So this is going to be 8 plus negative 3 to 4. We said that was 6. So all of a sudden I get all the way up to 14. Okay? Now, hopefully that makes sense. You're just plugging in values for x, evaluating. Derivatives, more complicated than it was. Why? If I take the derivative of this entire thing, I got to take the derivative of both 2x and my accumulation function. So the derivative of 2x is 2. The derivative of my accumulation function, like the derivative of my antiderivative, it makes sense, is f of x. This is f. If I asked what is h prime of negative 5, it's 2 plus f of negative 5, not just like this 2 value, which we had in the previous page. So it's 2 plus 2, which is 4. I'm not having to worry about going backwards because the f value is just whatever the value is of f. It's just like essentially what is the derivative value. H prime of 1. Well, again, 2 plus f is h prime of x. So h prime of 1 is going to be 2 plus f of 1. I found what f of 1 was earlier. It was 2. I went down 2 over 1, down 2 over 1. So this is 2 plus 2 again, which is 4. H prime of 0. It's not 0 plus, it's 2 because the derivative of 2x is just 2. Let's just make sure we write that down. H prime of x is 2 plus f of x. Okay? So 2 plus f of x at 0. H prime of 0 is 2 plus f of 0 is 4. So that's 6. H prime of 3, 2 plus f of 3. I need to find what f of 3 is, apply the slope, down 2 over 1. Oh my goodness, that's when h prime is 0 at 3. But that's not where we have a 0. This is what makes things complicated. And I'll show you when we do the relative maxes and mins and stuff like that. Okay, h double prime values. H double prime values. Well, let's look. If I took the derivative of h prime to get h double prime, the derivative of 2 goes away. The derivative of f, f prime. So, just like this previous problem, where like g double prime is f prime, that's the same thing for this because the derivative of 2 now just goes away. So the concavity of this h function is going to be the same as the concavity of the g function from earlier. So I'm just going to use the values from before. I didn't use the same values, so whatever. Negative 4, 1, 2, 3, 4. What is the slope of this line segment? F prime's slope at negative 4 is negative 1. Go down. Oh, down 2 over 2. Yeah, negative 1. H double prime of negative 1 is f prime of negative 1. What is the slope of this line segment? Up 4 over 3, negative 1. The slope here, that point is at 8/3, but the slope is positive 4/3. H double prime of 0, f prime of 0. What is the slope at 0? Does not exist because it's a sharp point. That's a quick little reminder from the back in the day. H double prime of 3 is f prime of 3. The slope of this line segment is negative 2. Okay, Now comes the tricky part. Relative maxes and mins. Always in the past, every single time in the past, we just said, oh, okay, when do we cross the x-axis? And it's like at 2, that's going to be my max of f if this was f prime. Or at 2 in the previous problem, that was the max of g. This is different. Relative maxes and mins when h prime changes sign. That's when it like passes through a 0. Well, h prime is not just f. H prime, we said, is 2 plus f. So what does that mean? Well, you could think of taking this graph and shifting it up 2. And that's the graph that you need to look at. That's going to tell you how much you're increasing or decreasing. But what I like to do is say, okay, well, I'm trying to figure out when this like passes through 0, when it crosses the x-axis. Well, if I set this equation up, I realize when f of x equals negative 2, that is when h prime will equal 0. So it's almost like, don't look at the x-axis. Instead, look at this new line here at y equals negative 2. This is your key to understanding when g is increasing or decreasing. When h is increasing or decreasing. When f is above this line, h prime is positive. When f is below this line, h prime is negative. That 2 plus f being positive, or the 2 plus f being negative. So the key is this intersection. Now, hopefully we don't have to do too much work in terms of applying a slope. We know this line segment's slope is negative 2. I go down 2 over 1. This is at 3. At 3, I hit negative 2. So actually what goes down on a sign analysis of h prime again being 2 plus f, is 3. 3. Because that's when f equals negative 2. That's when 2 plus f is going to change signs. It's above y equals negative 2 until 3, which means h prime, the 2 plus f, is positive, and then it is negative after. That means h, which is 2x plus the accumulated area, is increasing until 3 and then decreasing after 3. X equals 3 is our only max. It's going to be both the relative and the location of the absolute max, because it's just going to go up and then it'll go down. So if I ask to find what is the absolute max value, the max value I know is at x equals 3, because h prime is positive from negative 5 to 3, and then h prime is negative from 3 to 4. We're only decreasing between 3 and 4. That's when like our negative area cancels out, like the 2x being added. So all I need to do is find what h of 3 is. I found what h of 3 is earlier. Nope. All right, let's find it. Okay, so go back to just like the equation. H of 3 is 2 times 3 plus the area from negative 3 to 3. Becomes a little bit more complicated of a calculation. This is 6 plus. From negative 3 to 2, this area was 10. But from 2 to 3, I need to find this area of this triangle right there. I'm over 1 down 2, so this is down 1. That's negative 1. So 10 plus negative 1 is the area from negative 3 to 3. This gives me 6 plus 9, which is 15. That's the absolute maximum value. The min, again, is either at our endpoint x equals negative 5, since there's no relatives mins, or at our endpoint x equals 4. I kind of know by looking at this that I'm increasing a lot from negative 5 to 2, and then I'm just decreasing a little bit. If you like look at like kind of the areas above and the area below, you can see like I go up a lot, I go down a little bit. Just find the values though, just to confirm things. H of negative 5, I did find h of negative 5. it was 4. So I start at 4. I increase till I get to the value of 15. And then I know that I'm going to decrease just a little bit to get h of 4. I found h of 4 was 14. Okay, so 4 goes all the way up to 15, and then I go down a little bit to 14. Points of inflection, same as the previous problem. Because h double prime is the same as f prime, points of inflection are at -3 and 0. Because that's when h double prime, which equals f prime, changes sign. -3 goes from negative to positive, 0 goes from positive to negative. We can sketch h. This is what h is going to look like if I put everything together. This is just like what we did back in the day. Only we now know that areas under derivatives gives us changes in totals. I start at a y-coordinate of 4, right? At -5, I got 4. So I start at -5, 4. Let me put that down here because I'm going to go up a lot. I'm going to be increasing concave down until -3. At -3, I get hold on a second. What did I mess up on? Oh, I totally screwed up earlier. Sorry. I don't start at 4, go up to h of -5 I found earlier. It was not 4. That was h prime of -5. H of -5 was -12. My bad. I start all the way down at -12. I go all the way up to 15. And then I just go down a little bit to h of 4, which is 14. All right. So that's the number value. That makes sense. I'm adding a lot of area above that -2. So at -5, I start at -12. Increase concave down until -3. At -3, I have -6. Increase concave down that much, I add 6. And then I get to h of 0. H of 0 is 6. I'm increasing concave up until that, because this is positive. And then I'm increasing concave down until my max at 3. Increasing concave down until I get to 15. And then I decrease concave down until 14, just a little bit. Knowing areas helps us understand changes. This is a little bit more complicated because it's not just like the area, it's 2x plus the area. But just like go with like, all right, I just have to do this and I'll get the answers. Okay? All right, write an expression without an integral for the following. So this is one of those things where like we can't use a calculator. We go back to understanding that like we could take the antiderivative and find the change in the antiderivative. That's like we use our calculator to find our area under our derivative. If we can't use our calculator, we just have to take the antiderivative. So the antiderivative of sine is negative cosine. Keep the t, but when I plug in 0 and x, the t will go away. This is the whole reason why the derivative of that integral changes from f of t to f of x. When I plug in x, I get negative cosine x minus negative cosine 0. This is the whole like x of b minus x of a. Only we end up with a variable. Cosine of 0 is 1, so this is minus a -1, so this is negative cos x plus 1. 2t from 1 to x, antiderivative, t squared. Again, we should have a plus c, right, when we take an antiderivative, but we know it'll go away. when I subtract. So I just kind of ignore it. 1 to x. I get x squared minus 1 squared. Okay, look at this one. Antiderivative of e to the 2t. Do you remember that it's e to the 2t times a half? Because we need to undo the chain rule because this is t to the first and this is a coefficient. Maybe you remember, maybe you don't. Probably don't, but now you remember. C won't matter. This turns into 1/2 e to the 10th minus 1/2 e to the 2x. All of a sudden, the x is on this side because it started at the bottom. This is important when we essentially do the second fundamental theorem of calculus. It's a rule that you'll just learn, but the rule comes from the process that we just did, which is if you took the derivative of this, it's like taking the derivative of this. If you took the derivative of this, the negative cos x's derivative turns into sine x. The derivative of this constant turns into 0. This is why we say the derivative of this accumulation function with any number, doesn't matter what it is, to x, of any function with a t, turns into just f of x. It's the derivative of an antiderivative. It should make sense, but a lot of people get tripped up with what is this number? What do we do with it? Well, it's like it will go away when you take the derivative because you take the antiderivative, you plug in the number, it's a number. Same thing here. I can just say this is e to the 2x from this one. I should have had these flipped, but whatever. I can just say this is e to the 2x because just like this, if these were flipped, we'd have our expression. Then when we take the derivative of this, the derivative of that is 0. So it goes away. I guess I just showed you like the first example. Like if you understand how this turns into this, and then if you take the derivative of this, the 1 goes away and it just leaves you with what you started out in the side. The 0 doesn't matter. Hopefully that helps you with things. So this is just e to the 2x. This, again, the pi doesn't matter. Unfortunately here, I can't take the antiderivative. Like I can't do the steps of taking the antiderivative because of this product. So you just have to go with like, oh, derivative of the antiderivative. This number doesn't matter because it's like I'm going to take the antiderivative of it. I'm going to plug in pi. That's a number. Take the derivative of that, goes away, 0. So that's why I know it's just going to be the derivative of this, x squared minus x cubed sine x. The t's go away, get replaced with x's. Now, what if it's not just x? What if it's something other than x? Show you this one, okay? Like if I took the antiderivative of sine, it's negative cosine, t plus c. Find the change between 0 and x squared. Well, again, the c is going to go away. Watch what happens. I get negative cosine x squared minus negative cosine 0. That's negative cos x squared. Again, this is plus 1. What we're going to do next is take the derivative of this. Well, taking the derivative of this is just like taking the derivative of that because I just like rewrote this to be that. If I took the derivative of this, I have to realize it's the chain. And when you take the derivative of the outside, the negative cosine's derivative turns into positive sine, okay? But you got to worry about the derivative of the inside, which becomes a 2x. So if you did the previous 3 problems, it's like, oh, it's easy. If you're taking the derivative of the integral, just the x replaces the t. So it's like, oh, the x squared is going to replace the t. Not really. It's the x squared will replace the t. But then I need the derivative of the x squared after it because of the chain rule. Now, what about this 1, which comes from the 0? It goes away. So it's really the same thing as like the number doesn't matter. But the rule, I don't want to say it's a rule, it's just what you kind of figure out, is that if you start with any number, go to a function of f of t dt, and you're taking the derivative of this. You get f of h of x times h prime of x because of the chain rule. Now notice it's not f prime of h of x times h prime of x, which is like what the chain rule is, because it's like I'm taking the derivative of the antiderivative of this. So it goes back to where I start. Here, e to the 2t, the antiderivative is 1/2 e to the 2t. From 1 to sine x, The plus c will go away. That's a sine x. So this turns into 1/2 e to the 2 sine x minus 1/2 e squared. Now, okay, if I took the derivative of this, which is like taking the derivative of that, notice we have a chain. We end up having this, whose derivative is 0, because this is just a number. But this derivative has an outside and an inside. The outside is like 1/2 e to the power. The derivative of 1/2 e to the power is just 1/2 e to the power. The constant just stays the constant. The power is 2 sine x. The derivative of 2 sine x is 2 cos x. So we can see why this rule works. If you're taking the derivative of the accumulation function with something other than just x, you plug that in, 1/2 e to the sine x. Or should it be 2 sine x? Why did I put 2 sine x? Oh, because it's e to the 2 sine x. Okay, good. Times the derivative of that. Now I have a 2 sine x here. Do I need it? Well, watch, like the 2 in this 1/2 goes away. So it works out where it's like plug in sine x in for t, but then multiply by the derivative of sine x. That ends up being the rule. And you can see if you wrote the derivative of this, it's 1/2 e to the 2 sine x times 2 cos x. The 1/2 and the 2 go away, e to the 2 sine x cos x. That's where the rule comes from. If you have something that you can't take the antiderivative of, you got to just use kind of the rule. You just got to understand, okay, I'm taking the antiderivative. I'm plugging in x cubed. I'm plugging in 1. Then I'm taking the derivative. Well, the 1 won't matter because you're taking the antiderivative, plugging in 1, you're getting a number. The derivative of that number, 0. But when you take the derivative of the antiderivative with x cubed plugs in, you end up with this x cubed plugged in times the derivative of x cubed. So you end up with 3x to the 5th sine 2x cubed. All right. All right, we got some free response questions. Try to get through them fairly quickly. So this is like actual free response questions from actual past tests. So like this is something that you'd be ready to do for your test, which is coming up very shortly because it's a 2-lesson unit. Start with g of 2. G of 2 is the integral from 1 to 2 of f of t dt. From 1 to 2. Okay, this is a funky one. I'm going over 2, down 1. So down 1 over 2 is the slope. So that's down 1/2 over 1. So this ends up being at a y coordinate of negative 1/2, down 1/2 over 1, down 1/2 over 1. That gives me the 3, negative 1. So if I want to find the area from 1 to 2, this is a triangle, 1/2, base length of 1, height of negative 1/2. That ends up being negative 1/4. G of negative 2, 1 to negative 2. Okay, so I'm going from right to left. I'm going back in time. It's going to be the opposite if I'm going from left to right. I need to find the area from 1 to negative 2. Well, let's start with this triangle. This triangle is a height of 3, a base of 1. So it's 1/2 base times height. This is 3/2. This, okay, we have a little semicircle. We have to remember the area of a circle formula. Area of a circle is pi r squared. The radius is 1. Since this is below the x-axis, we will say this is minus pi. But again, I'm going from right to left. So even though I said the area is negative pi, I'm going to say it's positive pi because I'm going backwards, right? It's like I'm increasing, like g is increasing from negative 2 to 1. It's going up 3/2. If you want to go backwards, go down 3/2. It's decreasing pi. Well, if you have a value and you decrease to get to pi, and then you know that when you plug in 1, you get 0. You need to decrease by pi to get to 0. Where did you start? You started at pi. You started higher back in the day, or in the past, to get down to be 0. So this is why it's a positive pi minus the 3/2. Find g prime of -3, g double prime of -3. Well, if this is g, if g is the accumulated area, we find that the derivative is just f of x, and then the second derivative is just f prime. This is the whole, like, these problems are the same as what you've done before, except it's starting with big F and giving you regular F, instead of starting with questions about F and they give you F prime. And now that we know areas under a derivative equal changes in totals, we can find exact values. Anyways, g prime of -3 is just going to equal f of -3. F of -3, -1, -2, -3. Again, we have to use our slope to find this value. I go up 2 over 2, so this is just a slope of 1. So up 1 over 1, that's -3, 2. G double prime of -3 is the same as f prime of -3. The slope of this line segment is f prime. The slope of that line segment is 1. Determine the x-coordinate of each point in which the graph of g has a horizontal tangent line. G is going to have a horizontal tangent line when g prime equals 0. Okay, well, g prime is the same as f, so when f equals 0, let's just answer that part. When does f equal 0? At -1 and 1. For each of those points, determine if g has a relative max, min, or neither. Justify your answers. Well, let's look. If I analyze the signs of g prime, I can tell if g is going up or down. G prime signs tell me if g will have maxes or mins. It's the sign analysis. G prime is f. This is the derivative. We're given a derivative. So it has a 0 at -1 and 1. It's positive. These values of f are positive until here. They are negative until here. They are negative after there. That means x equals -1 is a relative max. Justifying your answers would be just simply saying g prime, which equals f, changes signs from positive to negative at that point. You have to write it down, unfortunately. Like, you have to write the statement down to be proper. I'm not going to worry about that for your test, but for the future, for the AP exam, unfortunately, you can't just be like, hey, look at this. Look at what I did here. That's why. You can't say, you have to say g prime changes sign from positive to negative at -1. And then 1 is a neither. Neither a max nor a min, because g prime does not change signs. When does g have a point of inflection? When g double prime, which equals f prime, changes sign. If we look at g double prime, which equals the slopes of f prime, of the slopes of f slopes f prime. F slopes are positive until -2. Sharp point, don't care. Goes from positives to now negative slopes. Okay, negative slopes. Now the slopes are negative. The slopes are negative still here until I get to this point right here at 0. At 0, we change slopes from negatives to positives. Positive slopes until here at 1, and then we change the negatives. Now, do the sharp points care? I don't care about sharp points. Don't worry about sharp points when it comes to like finding when signs change. You don't have to worry about it. Your answers are -2, 0, and 1. Those are your points of inflection. They didn't ask you for absolute max values. If I asked you, when is the absolute max value? You would say the absolute max value has to be at -1, because we increase and then we decrease. -1, it would be pi. Pi would be the absolute maximum value for sure. Now, the absolute minimum value, it's not going to be clear, because like compare this area to this area, it's probably going to be at this first point at -4, because the area from -4 to -1 looks to be bigger than how much we're decreasing from -1 to 3. Like, remember, the area under the derivative gives me the change in total. I decrease -pi -1, but I increase more than that. This is like a little trapezoid. You can find the triangle, the rectangle. You can find this. So I would say that the absolute minimum would be at -4. I would find that value. The absolute maximum would be at -1. And I probably would find g of 3 as well, just to confirm that this g of -4 is going to be a smaller value than g of 3. All right, so this is like, this problem right here is like what we did back in the day. This is the graph of f prime. You're asked questions about f, but now we can do more. We can't just say, oh, here's the relative max location in terms of an x, because we know now that the area under f prime tells me, the area under the derivative tells me the change in f. We have this initial condition. This is unlike the previous problems that we did where like we were given f, but in terms of an integral, and then the derivative that we are seeing, we knew the initial condition. This is different because they have to give you the initial condition. They're not giving you the integral. They have to tell you f of -2 is 7. That's your starting point. We're going to use what we've used in the past to find other values like f of -6 and f of 5. Like, how do I find f of -6? Well, I know what f of -2 is. That's my initial value, my starting point. That's like knowing your starting point is at 1, and if you plugged in 1, you get 0. That's like your starting point for there. You have to be given a starting point here. It's like the rate problems, like how much water starts in the tank. That's the same thing. F of -6 equals f of -2 plus the displacement. This is our friend. The area under our derivative gives us a change in f. Area under f prime now tells us how much we increased or decreased or how much we displaced. All right, so I have to go from -2 to -6. Why? Because this is the initial point that I'm given at -2. So -2 to -6, the base length is 1, 2, 3, 4. The height is 2. So this is just going to be +4. But since I'm going from right to left, I am going to increase 4 to get to 7, right? What does f of -6 have to be? 3. So that 3 plus 4 gives me 7, right? Like this is f prime is positive. I'm increasing by how much? This much. So you can do the math though. 4 plus this is 7 plus -2 to -6 is opposite of -6 to -2, 4. I have to start at 3. Add 4, I get to 7. It's the same thing as motion, moving right and left. Now we're just applying it differently. F of 5 equals f of -2. I start at 7, and then how much do I displace between, the time of -2 to 5? Well, from -2 to 5, I have to find this area. This is a circle with a radius of 2. So this is 4 pi, but it's, oh my gosh, I totally made a mistake back here. This should be pi over 2. It's half of a circle. Holy cow. Pi over 2. Wow. I'm sorry. My bad. Half of a circle, pi r squared divided by 2. Pi times 2 squared divided by 2. 2 pi. It's underneath the x-axis, so consider it negative. And then we have a triangle base length of 1, 2, 3, height of 1, 2. So this is 3. So I have my starting point, my initial value, like my initial position at 7 when time is -2. I add my displacement, which is -2 plus -2 pi plus 3. So I get 10 minus 2 pi. I go down 6.28, and then I go up 3, starting at 7. So I will end up lower than here. That's important to know if I'm asked for like an absolute max. You can tell like this area being bigger than this area, I'm going to go down more than I go up. When is f increasing? F is increasing when f prime is positive. F prime is positive. Here's f prime. Again, this is the derivative. This is velocity from -5. Is that -5 or -6? -6 to -2. And then from 2 to 5. Justify your answer. I just did. F prime is positive. That's justification. All right, absolute minimum. Here we go. Absolute minimum value. Let's look at our candidates. f prime is positive until -2. It is negative until 2, and then it's positive from 2 to 5. Sorry, -6. What are our candidates? Well, here's a relative min. And you'd say f's got a relative min at 2. F prime changes signs from negative to positive. I'm only decreasing 2 pi. That's like 6.28. Well, from -6 to -2, I'm increasing 4. So let's see. I start at a point. I add 4. I start at 3. I add 4 to get to 7. And then I'm going to subtract 2 pi. So I'm going to go to 7, but then I'm going to go down 6.28. If I start at 3, go up to 7, go down to like point something, that's got to be my lowest point. Now, it's tough to say that and to word it. What's easiest is to just be like, hey, it can't be 5 because f prime's positive. I know I'm going up 3 after f of 2. It could be -6 and 2. Let me just compare the values, and this is the easiest way to kind of justify your answer. F of -6 I already found. F of -6 is 10 minus 2 pi. F of -6 was 3. F of 2 I know is going to be the minimum value because it's f of -2 plus the integral from -2 to 2. This is going to be 7 of f prime, the derivative under f prime. The area under f prime gives me to my displacement. This is going to be 7 plus -2 pi. This is less than this. This is why this is the winner for your absolute minimum value. The way to justify is really actually tedious, and it's easier to talk through it, but to write it out, you'd be like, all right, f's got a min either at 2, because it's a relative min, f prime changes sign from negative to positive, or at an endpoint, but I know it's not 5 because f prime is positive from 2 to 5, which means f goes up from 2 to 5. Okay, so I know it's not 5 because 2's got to be a smaller value because you go up 3. What is -6? You could say like, well, I know I go up 4, but then I go down 6.28. If I go up 4, then down 6.28, I got to get to a point that's lower than where I started if I go up 4, down 6.28. You could say that, or you just be like, well, here are my 2 candidates. Here are the values. This one wins. Whatever's up to you. F double prime of -5, F double prime of -5 will equal the slope of F prime at -5. The slope of F prime is down 2 over 1, 2, 3, 4. So it's a half, -1/2. It's no big deal. Then F double prime of 3 is the slope of the tangent to F at 3, 1, 2, 3. Sharp point, undefined, does not exist. They want does not exist. Does not exist, it's a sharp point. All right. Okay. Last one. Be careful. Be careful. Be careful. Careful. 2x. There's a 2x here, just like we did in the previous problem. 2x here. Sometimes it's just x. Sometimes it's 2x. Sometimes it's the function, the integral minus x. You got to be careful with all that stuff. This is where it's like, oh, don't look at the y-axis. The y-axis might be misleading in terms of how much we're increasing and decreasing because of this 2x. Turns out we need to focus at the line y equals -2 because the derivative of this is 2 plus f. But whatever, let's just go step by step and just do the process, get the answers, go with it. So g of -3 is what I'm trying to find first. That's 2 times -3 plus integral from 0 to -3 under f. I gotta finish this pretty soon. 0 to -3. So I got -6, 0 to -1, 2, 3. So this is a quarter of a circle. So this is a quarter of a pi times 3 squared. So that's 9/4 pi. But I'm going from right to left, which means like it's the opposite. I have to add 9 pi over 4, if we thought about it kind of like that, to get to their next value, which means if you go backwards, you have to subtract it. So this is minus 9 pi over 4. What's g prime of x? If you took the derivative of g, it's not just f, it's 2 plus f. Be careful. And then g prime of -3 is going to be 2 plus f of -3. F of -3 is 0, 1, 2, 3. So this is 2. When does x have an absolute max? All right, they go right off. They go right into the tough stuff. Okay, absolute max. Well, we need to analyze the signs of G prime, right? Well, G prime is not just f. You don't just say, oh, it's going to be at this location. No, because G prime is 2 plus f. It might be 1 plus f, depending on the situation. It might be f minus 1, depending on the situation. You got to figure out when this changes sign. Well, that's when f equals -2, just like your previous problem that we did. We need to look at this line. That's when G prime can change signs. Actually, the area above this is going to tell us how much we're increasing and how much we're decreasing. You don't have to worry about that. You just like find the area by doing this. But that's like if we move everything up. Anyways, it's positive until this intersection. What is this intersection? This is the tricky part. We have to apply the slope of this entire line segment to find what is this x coordinate. You can assume it's 2.5, but be careful. Let's see. I go down 1, 2, 3, 4, 5, 6 over 1, 2, 3. So down 6 over 3 is the slope of -2. So I'm going down 2 over 1. Okay. That's the same as like down 1 over a half, right? Like that's different ways to get 2. So down 2 over 1, down 2 over 1, down 1 over a half. Yeah, 2.5 is correct. 2.5, and then G prime is negative. I just want the x coordinate. Thankfully, I don't have to find the value. When we have an absolute max, I know x is 2.5 is definitely the absolute max because G prime is positive from -4 to 2.5, and then G prime is negative. That means G, this function, is going up and then going down. That has to be the max. Point of inflection, G double prime. Okay, what's G double prime? If G prime's 2 plus f, G double prime is just f. Again, like all of a sudden that 2x won't matter when it's talking about points of inflection. Since G double prime equals f prime, let's look at the slopes of f prime. They're positive till here, which is kind of like a vertical tangent, so it's undefined. But then after it's positive, so you don't have to really worry about that. It's positive until 0. It's negative after 0. X equals 0 is when G double prime, which equals f prime, changes sign. Find the average rate of change. Okay, this is not find the average f. If it was like find the average f, that's 1 over b minus a, integral from a to b of f. But it's average rate of change. This is when we go back to rates of change or slopes. Average rate of change is a slope of a secant. So we need f of 3 minus f of -4. Remember this formula for the slope of a line? This is the slope of the secant. This is the average rate of change. So I have for f of 3 is -3. F of -4 is -1 over 3 minus -4, which is positive 7. So I've gone over 7 units and I've gone down 2. Okay, so -2/7 is the average rate of change. There is no point C for which f prime of C equals that average rate of change. What? Explain why this does not contradict the mean value theorem. Oh, there's the key, mean value theorem. Oh, we're talking about the mean value theorem here. What the heck is the mean value theorem? The mean value theorem was that theorem. There's 2 theorems, right? The intermediate crosses points. The mean talks about slopes. The mean value theorem says like, oh, if you have 2 points and you connect them smoothly, that slope between those 2 points, you're guaranteed to have a tangent slope that equals that secant slope. That's the whole I rock equals A rock. And it's like, okay, that's guaranteed to exist if something's true. You were told, hey, there is no derivative of f that equals -2/7. Why is that not a bad thing in this situation? We got to remember the mean value theorem only works if The function is differentiable. If there is a sharp point when you connect these 2 points, you are not guaranteed to have that tangent slope there. Okay, so here's an example, a sharp point, all of a sudden I don't have that tangent slope that equals that secant slope. Why does this not contradict the mean value theorem in this situation? That's a sharp point, and that also is a vertical tangent. There are 2 locations where our derivative does not exist, which is why we can say, since f is not differentiable, on our entire interval, therefore, mean value theorem cannot be applied. All right, this was good homework. Glad I did this video. Wish I kind of did more videos this year. I'm redoing motion. I think I can do it better next year. You guys show me that. I show myself later.